Welcome back. Today we're going to look at the introduction to conservative fields, and this actually is a return to conservative fields because another name for conservative fields is gradient vector fields. And this loops us all the way back to the definition of the gradient when we're working with surface functions and the directions of greatest increase. So the questions that drive us in this section are the following. First, can we integrate vector fields algebraically like we integrate scalar functions? This is kind of a weird question, but it's so fundamental to how we think of conservative vector fields. Is there a way to come up with an antiderivative to a vector field, a vector function, that somehow undoes the differentiation? And by differentiation, we mean the gradient. And so can we undo the gradient in some way? Yes, if the field is conservative. So the second question, when does a vector field preserve the same work along any path between 2 points? We've seen this example of work being calculated along multiple paths. Is there a way that we can tell when the work done is independent of path, when we can choose the simplest path for us instead of a path that has a minimum or maximum work involved? And the answer is yes. When does the answer is when the field is conservative. You'll see your pattern here. And then third, do all vector fields point in the direction of greatest increase of some potential surface? Is there a link between a vector field, the flow lines we see, and a surface underlying that? The answer, no. Only for conservative vector fields. So you can start to see why these conservative vector fields are so special. You may say, well, what special properties do these conservative vector fields? Let's see together. Okay, so that is the introduction of why we care about conservative vector fields, because they are at this juncture between imagining vector fields as if they are functions that we integrate in some way. And to start us out, we have the fundamental theorem. We already have one of calculus. This one is specifically for line integrals, a fundamental theorem of line integrals. It says that if your vector field is described by a gradient of a potential surface, this surface can be of any number of variables or any kind of variables in any coordinate system. If your vector field is described as a gradient of some surface on an open connected region, connected here refers to the region being one piece, not multiple pieces, containing a piecewise smooth curve C, then the integral of that vector field dotted with dr, or the work done by the vector field in the direction of the curve C, is equal to the evaluation of the potential surface at the end point of your curve and at the beginning point of your curve, the end point and the start point. So n minus start. You can think of that as b minus a in a sense. Okay, so how do we prove this idea? Well, we're going to use two major things. One is the chain rule for this multivariable function, p. Assume that's in 2 dimensions. You can expand it down to 3 or further. It's not that hard. And the fundamental theorem of calculus. Again, this is a fundamental theorem. It's tied directly to the fundamental theorem of calculus. So first, we start out with highlight a little bit here. First, we start out with replacing the vector field with the gradient of a surface. And then we write out each of these pieces in terms of their components. So the gradient in 2 dimensions is broken into its two x and y partials. And then the r, or velocity dr piece, is broken into the velocity vector and dt. So the velocity differential is your velocity times dt. And now when we dot those two vectors together, we'll get p sub x times x prime plus p sub y times y prime. But it makes a lot more sense intuitively if you write those out in terms of the partial and differential fraction notation that we owe to Leibniz. So the partial of p in terms of x times dx dt, notice the x is there, and then the partial of y in terms, partial of p in terms of y times dy dt, notice the y right there. This is the accordion fold of the chain rule for a multivariable function. You can think of this as coming from a beautiful little tree. I'll draw it in green too. So there's p on top, breaks down to x and y both connect down to t. So because there's a common variable at the bottom, we can write the sum of the partials down the tree on both sides in terms of t as one single derivative. And it's a full derivative. It's the full derivative of the overall surface in terms of time as we travel along it. And so because we're integrating a derivative in terms of t, we can apply the fundamental theorem of calculus to undo that derivative and evaluate our function at the two endpoints. B endpoint first, and then subtract the A endpoint, which allows us to think of this as the surface evaluated at the end of the curve and then the start of the curve. Okay, so that is a very quick proof of one of the really fundamental theorems of this chapter, relying upon another fundamental theorem of Calc 1. So let's slide on down to see what we can do with this. Well, first, let's go over what it means. The corollary to this statement is a number of theorems in the textbook. I've summarized them in one long strain. The following are equivalent to f being defined by a gradient, or being a gradient vector field. On an open, connected, or one-piece region, one piece, and simply connected, that one piece has no holes in it. Open, connected, and simply connected region containing a piecewise smooth curve C. Now, piecewise smooth means that it's differentiable along little pieces. So you can have a line connected to another line, connected to another line. That's piecewise smooth, even though there's non-differentiable cusps along the way. Now, this is important because we're integrating along that curve, so we can deal with the piecewise smooth sections. And the reason why the connected and simply connected is important is that we have one piece. We don't have to hop from one piece to another. Our curve is contained within one piece. As simply connected means that our curve doesn't have to go, can't run into a hole as it's traveling within our region. And if we wrap around our curve and kind of draw it, move it around, topologically speaking, move it around the space, we never snag a hole in a sense. Okay, so the four things that are equivalent to it is first, that f is ascribed as a conservative vector field. So there you go. That is the definition, in a sense, of a conservative vector field, is that it, not the definition, but equivalent definition, that it's defined by a gradient of potential function. What makes it a conserved vector field is that it conserves certain quantities. And one of those things is that work is independent of path. So the kind of the meaning of being a conserved vector field is that work is independent of path. We know that's true as long as F is a gradient vector field, and only if F is a gradient vector field. And if you take that idea a step further, we can evaluate an integral of F dotted with dr with a circle around it. Now, this is interesting notation. It's not necessary notation, but it's helpful. That circle tells us that the curve C is closed. So if you want to think of it another way, the first one is the work done on any curve versus the work done on a closed curve. And sometimes you'll notice that these circles have little arrows on them, which means that it's oriented counterclockwise. So that will tell us a certain direction of the curve. And orienting counterclockwise restricts the kinds of parameterizations you can do and keeps things as unified as possible. So any curve, any orientation can be described in terms of integral sub C. A closed curve and counterclockwise orientation of the curve is described with a circle, a closed circle around that integral, and it's representing not necessarily a circle, but a closed path oriented counterclockwise. And if F is conservative, then work is independent of path. And if you're starting and stopping at the same point, then your work is 0. There we go. Third, each pair of mixed partials based upon a common perpendicular basis direction are equal by Clairaut's theorem. Now this is interesting. We don't see this idea really doing too much in 2 dimensions, but in 2 dimensions you can think of this as, 2D, we just have F and G, and the perpendicular direction that's common to them is K hat. And so by K hat, we have the mixed partials. So the partial of G, the second or Y component in terms of X, is equal to the partial of F in terms of Y. Mixed partial means you're taking the other derivative of this variable's component. So the X derivative of the Y component, G, and the Y derivative of the X component, we call F. There we go. In 3D Cartesian, we have something like F, G, H. And for that, you pick a direction. There's 3 different common orthogonal directions. Let's just try I hat. So I hat is the X coordinate and direction. So we look at what combinations are perpendicular to it. Well, it's the Y direction and the Z direction. So we take the mixed partials of those 2 corresponding pieces. So for H, the Z component, we take the Y partial, and that is equal to G, the Y component's Z partial. So the mixed partial just means that you take a pair of components that are orthogonal to some common direction, I hat, and then you equate the mixed partials. The y partial of the z component is equal to the z partial of the y component. And we can do this for j hat and k hat if we need to. So that's what this third statement means. And the fourth one is that the curl of a vector field is equal to 0. And this is a direct consequence because the curl is actually equal to the difference of the mixed partials in each of those orthogonal directions. So in 2D, the curl of f, we usually write it as, well, the curl of f is equal to g sub x minus f sub y k hat. That's what we ran into when we looked at the gradient way back in the chapter on multivariable functions. And in 3D, we can extend this outward. The gradient of f, sorry, the curl of f, the gradient cross the vector field, is equal to a combination of these differences. And we just talked about the I hat component. That would be h sub z minus g sub, h minus g, we'll start with that. And then mixed partials, so h sub y, g sub z. And then with the j hat component, we again switch the sign. And for j, the two components that are perpendicular to the y direction is the z direction and the x direction. And so we take the mixed partials, x partial of the z component and z partial of the x component. And then finally, we look at the k hat or z direction, and the two components that are perpendicular to that are the x component and the y component, which is g minus f. Take the mixed partials. This is the x partial of the y component we call g, and the y partial of the x component we call f. Whew. So that, by construction, is what the curls are. And when the mixed partials are equal, when your vector field is conservative, when it's defined by a gradient, the curl is 0. Okay. Now, we get through that theory, getting all those ideas together. Let's look at applying it to determining when a vector field is conservative and how to use it, how to find that conservative, how to find that potential function. So first, we're going to look at the test for conservative vector fields. And this test really is looking at the mixed partials. It's based upon the theory we just talked about. That third step of the theory of the related components based on Clairaut's theorem really just says that g sub, well, we say g sub x equals l sub y, but if we think about that in terms of what f and g are supposed to represent, how do we prove that? Notice that f is supposed to represent the x partial of that function. So then f sub y is really p sub x sub y. And g is supposed to represent the y partial. So g sub x is p sub y sub x. Are these two things equal? Yes, says Clairaut's theorem. Whenever you have a twice differentiable surface, the order of mixed partials does not matter. Mixed partials are always equal. You can reorder those variables on the bottom any order you want. You could, this could go out 10 different partials. You just reorder all over the place. As long as the partials are continuous, they can be done. We don't have any discontinuities to worry about. Then the mixed partials are equal. And that theorem, Clairaut's theorem, is exactly how we can test any vector field. And you know what? We don't have to restrict ourselves to working in Cartesian. We'll also see this example in polar and in spherical a little bit. But let's start out in Cartesian just to demonstrate a little bit. So here is our F and our G. We check G sub X equals 1 and F sub Y equals 1, and so they are equal. Therefore, F is conservative. Now, this same test can be utilized in polar coordinates. It's a little bit different, though, because as we saw before, the gradient in polar breaks up into the radial direction times the r partial of the surface plus the angular direction times the theta partial of the surface divided by r. Notice that whenever we're looking at derivatives in terms of an angle, there should be some linear factor paired with it. Okay, so how do we check to see if the mixed partials are, how do we check to see if it's conservative? Well, we verify that the mixed partials are equal. Notice that in this case, we are looking at the partials in terms of r and theta. And so if m represents p sub r, m sub theta is p sub r sub theta. There we go. And the same way, if n over r is equal to p sub theta over r, that just means that n is equal to p sub theta, then n sub r is p sub theta r. Are those equal? Yes, says the Clairaut's theorem. And that formation of the scalar for the theta component is exactly why we always write our polar vector fields with something n divided by r, so we can match up a grouping of terms with the theta partial. So let's check. On this particular function, vector field, it's complicated, right? Much more complicated. We find that we can deal with much more complicated vector fields if we can find symmetry to simplify it down. So the first thing we do is we check to see what component of this vector field is moving in the radial direction. How much of the x component is in the x direction? Minus 2x. Let's try that again. So how much of the x component is in the x direction? Minus 2x. There we go. How much of the y component is in the y direction? Minus 2y. And notice they have the same scalar. And so we get a minus 2x and minus 2y. We factor the negative 2 out. And in a similar way, we look at how much of the x component is going in the y, or shall I say negative y direction, and how much of the y component is going in the x direction. And we get these two pieces out. And we remember that r hat is xy divided by r, and theta hat, theta direction, is minus yx over r. So we're using these principal directions to recognize components that are either moving in the radial or angular directions. Okay, so now we break it into two pieces. We factor out the radial and angular directions. So notice that on the bottoms we have 2 copies of the radius. So we use 1 copy of the radius for our unit vectors, and 1 copy of the radius is left out. And so in the first term, we factor out a -2 from the top and an r on the bottom. From the second, or theta term, we factor just a 1 on top and an r on the bottom. That 1 on top is because we already have that -y, x form of the positive angular direction. Okay, so that's just how we form it in polar coordinates to simplify through the symmetry of the problem, because I don't know about you, but I don't want to start taking x and y partials of that thing as it is. Okay, so let's check to see if this is conservative. We want to check to see if n sub r equals m sub theta. So n equals 1. So n sub r is 0. M is this whole thing. So m sub theta equals, well, if we look at that whole thing, -2/r, there's no theta. Also 0. So the mixed partials are equal, which means that f is conservative. So all those properties of conservative vector fields apply to both of these vector fields. Okay, so let me clear that up and move on to some 3-dimensional examples. So in 3D, we want to do a similar thing, except we are going to equate the pairs of partials together in Cartesian. So the first pair corresponds to the k hat direction. That's the 2 components, the y and the x, that are perpendicular to the z direction, z component. The second one has an h and an f. Think about that for a second. Missing the g, which is the y component, so this is perpendicular j hat. And then the last one has h and g, so z and y. We're missing x, so that is the I hat direction. Now, what we're looking at is rotation about those 3 directions. Rotation about k hat would be rotation in the xy plane. The rotation about j hat would be rotation around the xz plane, and then rotation about I hat would be about the yz, rotation in the yz plane. So that's kind of the idea behind it. Let's look to test if this is conservative. There's a lot of pieces. Let's identify those. There is, I should not do that. Here is F, there is G, and there is H. So first we check if G sub X equals F sub Y. So G sub X gives us a 2X. F sub Y gives us also a 2X. 2xy there. And so those match. Going on to the next one, we have h sub x equals, so we go to h sub x, that gives us a -2z. And then we check f sub z. F sub z only has a -z squared there, so that gives a -2z. Check. And then finally, we look at the last pairing, h sub y equals. So we go back to h, You see a 2y there, so we get just a 2. And then we check g sub z. Well, g has just a 2z there, so its partial is also 2. Boom! Whew. So that rather complicated combination of variables is conservative. It has a nice balance, and it allows us to find a gradient vector, in a sense. We can find a potential function whose gradient is this vector field. Running out of room to celebrate how conservative these are. Now, again, that conservative means that they're conserving energy, they're conserving quantities. They allow us to evaluate things independent of path. We're celebrating independence. So when you think about whenever we say F is conservative, just think we're celebrating independence from parameterization, independence from having to figure out how to follow a particular curve, independence from setting up a lot of these integrals. So really, I should say independence, independence, independence. Okay, and the last one here is radial. Now, this is a special case of a spherical vector field, and reason I want to point this out is that it comes up so much in applications. We really just have to talk about it. A radial field is one where there's only an amount pointing in the radial direction. So the vector field is only pointing outwards or inwards. And this would be paired with the r partial, r being the three-dimensional radius vector, r partial in the radial direction, r direction. And that is described as the gradient of that surface. Now, this surface can only be defined in terms of a radius because it's defined basically in circles as you go, or spheres as you go outward. It's defined by spheres, right? Each sphere has a different value, different surface value, hypersurface value in this case. Now, this kind of field, vector field that's radial, is conservative on this region D, if and only if, this is kind of weird, the phi partial of M is 0 and the theta partial of M is 0. It just means that when you're given a vector field that's moving radially outward, it cannot change in the phi or theta direction. It can only change in the radial direction. Okay, that's fair, right? We're assuming that our potential function is based only on r, not on phi and theta, and so that's basically it. Now, what's interesting is this is so much easier to check than these 3 pairs of mixed partials for regular 3D vector fields. So it's a celebration right there. And it's good because the vector field we're going to run into is a bit of a beast. Let's look at it. Boom. This right here is a description of the gravitational vector field. It has a constant out in front of g, the universal gravitational constant, m, the mass of the large object, let's say the Earth, and then little m, the mass of the little object, let's say an orbiting vessel or satellite, times the structure x, y, and z, and the x, y, and z direction components. That is a radial direction, divided by the square root of x squared plus y squared plus z squared, that which by itself is just capital R, raised to the 3rd power. So this is called the inverse square law. And we can't really see the square law, the squareness of it in Cartesian. We can only see the squareness of it when we convert it into spherical coordinates. And so, what is spherical coordinates? Well, it's just like polar coordinates with big R. Oop, let's get to drawing. Our hat is simply the position vector, x, y, and z. You can think of that x of t, y of t, z of t, sure, divided by the magnitude to make it a unit vector. X squared plus y squared plus z squared, all under the square root. So that is the radial direction in 3 dimensions. And so if we factor out one copy of the square root over here, we have 2 more left. And that's why we have an r squared at the bottom. That's what gives us this inverse square law. Now, is this conservative? Yes, definitely. Look, we have a, oh, this is confusing. There's a capital M, mass of the Earth. Quick change. How about mass of Earth? And then we go back and delete. Okay. Basically, what we're saying is the component multiplying, or the component applied in the radial direction is something, and we want to make sure that m sub phi, whoa, is equal to 0 because m is not defined by the angle phi, and m sub theta is equal to 0 because m is not defined in terms of theta. So we're good. So we know that f is conservative, which means we have independence of path. We don't need to follow any particular path to get from point A to point B. We just have to evaluate the difference of those points. And if we're traveling along a path that circles back, if it orbits back, then the work done is 0. Wow. So think about that. The work done by the work done by the gravitational field to move a satellite around the Earth is 0. Think about that. Just because the vector field is conservative, we know that orbiting satellites are done with 0 work by the gravitational field. In a sense, they are escaping, continually escaping Earth's gravitational field. That's fair. Whew. Okay, let me wrap this video up so you have the theory all nestled together, and we'll have another video that talks about the procedure of finding these these potential surfaces and using them to solve problems quicker. Okay.